Okay, so welcome to today's video tutorial. Today we're talking about null terminated strings. So terminated strings are what C uses in most cases for handling string data, right? It's what you'll find everywhere in Linux and other open source code like that. And it's also a major security issue. So let's get into it. We're on MITRE's website, and this is the CWE Index, basically the common weakness enumeration list. CWE 170 is improper null termination, and so basically C strings have all these different issues. There's it's actually a pretty long list of issues, and they all deal with the fact of how these strings are actually created and passed around and modified and all that sort of stuff. This is a subset of, in general, bounds checking issues. Bounds checking in general is problematic, and it's an issue that we've known about for quite a long time. In fact, if you go all the way back to 1961, C.A. Hoare was working on Algo 60, and they explicitly put in bounds checking into the language because they knew it was an issue. It kind of makes you wonder, okay, well, why does C have this issue, and why does Linux and all this other software use it? And the reality is that when these systems came out, for one thing, memory was not cheap as it is today. And so, one termination byte would be like less than 4 bytes for storing the length of a string, for instance. And that's only like one tiny difference. There's many different issues there. But if you go, look for man pages, like you do a man to a exec or man to whatever, you'll see practically every single call out there wants a null terminated string. Invars, null terminated strings. Even your main declaration, null terminated strings. So it's everywhere, right? And some people will say, well, Rust can fix this issue. It actually can't. So the strings that are inside Rust are okay-ish, but that doesn't mean that you're automatically immune from this problem, because if you have to write a device driver, or if you have to talk on the network, or if you're writing an operating system, or if you're writing a database, you're inherently dealing with this data at that memory level. And so Rust is not going to save you all the time. It will definitely save some photons, but not all of them. So it's one thing that you just need to work around. If you look at Git, for instance, Git has this kind of popular list of banned functions. So like string copy and string cache, string toke, and all this sort of stuff. This list is endless. It's just inherently a problem. So what we did recently, coming back to Nanos, was we got rid of a lot of these null terminated strings. We wrote our own little implementation. Before we talk about that, let's dive into what some of these problems actually really truly are, though. So we get into here, and let me just show you like this little program. So this is our classic C string. If we pull up hex dump on this, I want to show you what this looks like actually in memory here. So we search for AAA. All right, so we found it. This is where it's actually stored. And you can tell because it's 41, 41, 41, 41. That's the representation in memory of our string. And then you can see this 0 basically terminates it. So we know that's the end of the string, supposedly. And that's what it looks like in memory, right? So this is how a computer works. Computers operate on memory. Computers don't operate on these objects that we've created to say this is a string and this is a something else. Computers have no knowledge of what a string actually really is. They just operate on memory, and you really need to You need to understand that at the fundamental level to really understand the problem. So that's what it looks like in memory. But this is not the only way to store strings. In fact, if we go out here, we can look at this Pascal program. So this is what we call a Pascal string. And basically it's the exact same string. It's 4 capitalized A's. We're going to compile this. I'm going to show you what it looks like. So pull hex dump again. I type the more. Okay, so now you can see our 4 A's again, and you can see 41, 41, 41, 41. But if you notice here, we have 4. So what Pascal's done for us here is that they actually stored the size of the string as a prefix. And so there's various trade-offs here, but this is like a nice handy way to kind of, essentially know the size of the string. And we can kind of see this in action, because if we add more A's, 1, 2, 3, 4, we recompile this guy, and then we pull up hex and dump again, 1, 2, 3, 4. Now we can see our 8 A's, 1, 2, 3, 4, 5, 6, 7, 8. And then you can see the length has changed to 8. So again, there's many different ways of dealing with this. Now let's go into the problems. Okay, so I mentioned there's just like 1,000 different problems. I'm only going to show like one today. This is a function where it takes two pieces of input, and basically it looks to see if you have the correct password. The password might be the secret. So back in the day, video games used to be distributed via a disk or a CD-ROM or whatever, and then they would sell you a license key. And so back then, if you didn't have a license key, you might choose to do this little exercise and just create your own. So basically what this does is it looks at the password, sees if it's set to secret. If so, it says you chose wisely. If not, it says you chose poorly. Seems pretty basic. So we can say secret and then test. It says you've chosen wisely. Okay, great. What if I choose bad? Okay, so I chose poorly this time. Seems like it works, right? But the problem here, and I'll show you what the problem is. If we look at our little program here, this string copy, as it's copying stuff into buffer, it doesn't really check to see if the input that I'm giving it actually fits inside that buffer. And if it doesn't, what happens is that you can potentially overflow into something else. So if we pull up object dump on this guy, you can see where these things are stored. So buffer stored at 4010, and then pass is stored at 4016. And so they're only that far apart from each other. Essentially, they're right next to each other, you could say. So what happens if we put in more stuff? Well, I can show you. We do something like main, and then Bob, and then we do like Bob 1, 2, 3 Bob. Okay, well, so what happened here? It says I've chose wisely, but that's clearly not that's not what the password was set to. The password was set to secret. What happened here? What happened was when we passed in the Bob 1, 2, 3 Bob. If you look at that, I purposely made it this size, by the way. There's 9 characters here in each of these. We have 6. So if we overflow that, we actually start overwriting this other piece of memory. And that's how we can kind of bypass this. So this is, again, one tiny example. There's thousands of examples like this. And this is something that we decided to get rid of. Okay, so let's go back to our implementation. So I yanked this out of the Nanos source code just to kind of show you what it is. These are just some type defs that we have in Nanos, so I copied them in. But essentially, this is what our string is now, is this S string. And so we have bytes of length, and of course bytes is on side 32. And then we have our char star pointer to the actual string. We have a few macros that we have. So we have our asserts, and then we can define a string at compile time using some of these. We can check for null to see if it's a null. We can check to see if it's an empty just by looking at the length. We can also convert a C string to a SS string with this little function. Now, this isn't like super sophisticated, but it is better than what we had. And we've put this kind of everywhere. What's interesting is this is not something that you can immediately do for other kind of general purpose operating systems, because again, going back to those cases where all these syscalls expected and all these libc functions expected and all this sort of stuff. And so it kind of gives you this this sort of opportunity to kind of go in and fix things like this. Anyways, this was kind of a little bit longer than what I was thinking, but I hope this kind of gives you some background on why we got rid of these null terminated strings, and what that does for Nanos. Till next time, bye.